Let's continue number 15. You already know the statement, but still let's see what it was. We have a non-zero ring A here in which X is the set of all prime ideals. For any subset E of A, V of E denotes the set of those prime ideals that contain E inside of them as a subset. We have already solved parts 1 and 2. Now today we are going to solve part 3, where a family of subsets of A is given, EI, an indexed family indexed by some index set I. For each small I in this set, we have a subset EI of our ring A. Now this is what we have to prove. V of the union of the EIs equals the intersection of these sets V of EI. Here also I varies over I, here also I varies over I. In the solution, we first name this union. That way it will be easier to write. Let's call this E. Now, of course, we know that each set EI is contained in the union E. That is, EI is a subset of E for all I belonging to I. So, V of E will be a subset of V of EI for all I belonging to I. We know from our previous video why. Hence, obviously, VE will also be a subset of their intersection. It's a subset of each set, so their intersection would also contain V of E inside of it. To prove that the reverse containment is also true, we take any element here. Let J be any element in this intersection. Then J is inside each set V of EI for all I belonging to I. What does it mean? It means that J is a prime ideal of our ring A such that J contains EI. But that happens for all I belonging to I. So that means that J is a prime ideal of A such that J also contains the union of these EIs, which is our E. But then by definition of V of E, J is an element of V of E. So that's how any element J here is also here. So that's how this is also a subset of this. So the two sets are equal. That's what we wanted to prove. So this is the solution to part 3. And then we have part 4, where we have to prove these identities. V of J1 intersection J2 equals V of J1 J2, which equals V of J1 union V of J2, where J1 and J2 are any ideals of A, not necessarily prime ideals, okay, they are any ideals of A. We start the solution like this. We already know that J1 J2 is a subset of J1 intersection J2. So V of J1 intersection J2 is a subset of V of J1 J2. To prove that the reverse inclusion is also true, we take any element here in this set. Let J be any element in V of J1 J2. Then, by definition, J is the prime ideal of A such that J contains J1 J2. Instead of writing this every time J is the prime ideal of A, you can also write that J belongs to the set capital X, because that's the set of all prime ideals. Now next we take any element X in J1 intersection J2. Then X belongs to J1 and X belongs to J2, because that's what intersection means. Now because X belongs to J1 as well as J2, X squared would belong to the product J1 J2 by the definition of the product of two ideals. But because of this containment, then that means X squared belongs to J. And now you use the fact that J is a prime ideal. Because X squared belongs to J, so X also has to belong to J. This means that any element in this intersection is also in J. So the intersection is a subset of J. But then that just means that J is a prime ideal of A which contains this J1 intersection J2. So by definition of this V set, J belongs to V of J1 intersection J2. So now you see this one and this one. Any element here is also here. So this is a subset of this, just like this one is a subset of this. So that means we have the reverse inclusion as well. We thus have equality. That means we have got one identity. Now we go for the other one. Now next you note this. We already know that J1 J2 is contained in J1 as well as J2, and that is why V of J1 is contained in V of J1 J2 and V of J2 is also contained in V of J1, J2. So the union of these two sets is also of course contained in V of J1, J2. Now we want to prove that the reverse inclusion is also true, and that's why we take any element J in this set. So that just means that J belongs to X. In other words, J is the prime ideal and J contains J1, J2. Now our aim is to show that J is either in this set or this set. J is already a prime ideal. So that just means showing that either J contains J1 or J contains J2. But suppose both of these are false. J1 and J2 are, none of them is a subset of J. J does not contain any one of them. But then of course there exist elements A and B such that A is in J1 but not in J. That means A is in this difference set, and similarly B is in J2 but not in J. The existence of these elements tell us that J1 is not a subset of J and J2 is not a subset of J. But now you take the product of A and B, AB. After all, because A is in J1 and B is in J2, so AB by definition of this product will be in this product. However, the product is contained in J, and so AB will belong to J. But where is J coming from? J is coming from X, the set of all prime ideals. So J is a prime ideal. So because AB belongs to J, either A belongs to J or B belongs to J. Both of these things go against this very choices of the elements A and B. A does not belong to J. You see, A belongs to this difference. Similarly, B does not belong to J. So that is why we have come to an impossibility. And this has happened because of our supposition. So our supposition is wrong, i.e. we must have either J1 a subset of J or J2 a subset of J. But then if this happens, then J becomes a prime ideal containing J1. So J will belong to V of J1. Whereas if this happens, then J belongs to V of J2. And that's why in any case, J belongs to the union of these two sets. But recall where J comes from. J comes from this set. So that's how this becomes a subset of this. But the reverse containment is what we previously had. So combining this one and that one, we have equality, and that completes the solution. If you combine all the parts of this exercise, you would notice that this collection of the sets VE satisfy the properties of closed sets in a topological space on X. In other words, if you take complements of these sets, and then also you are going to get a collection, that collection is a topology on X, and that topology is called the Zariski topology on X. With this topology, the collection of all prime ideals of A is called the prime spectrum of the ring A, and it is denoted like this, spec of A.